Hello and welcome. This is again kind of a weird additional a weird additional video because it's not a topic on its own. Now, something I want to talk about today is, obviously you've guessed from the title of the video, which is absolute zero. Now, in this video I'm just going to be explaining what is meant by absolute zero and how we calculate it. In other words, why it is what it is. Okay, now the first thing I want to state is absolute zero is the same for any gas and any type, okay, presuming it bases on the ideal gas laws. Okay, now the theory of absolute zero states that a gas will reach this, write this down, absolute zero. Okay, a gas reaches absolute zero when there is no kinetic energy in the molecules. Okay, so how are we going to use that little bit of information to be able to help us work this actual figure out? Because the value of absolute zero is minus, for any gas it's the same, it's minus 273 degrees C, or in other words 0 Kelvin. Okay, now that's a little bit of information there. Okay, so as I say, going on from this idea, there's no kinetic energy. In other words, obviously kinetic energy is dependent on mass and velocity, so obviously if there's no, well, it has to be a mass, so there must be no velocity then for it to be zero. Okay, so in other words, if there's no velocity, there's no movement of the particles. Okay, and if there's no movement of the particles, they're not pushing against each other, they're not trying to spread out, there's no force pushing outwards because they're not bouncing against each other, hence the key word here is there is no pressure. So because there's no kinetic energy, there's no movement of the particles, so politicians, there is a lot of that, no movement of the particles, so there is no pressure, unlike when you sit your exams. Okay, so the essence is there's no pressure. So let's think of the two factors we can observe here against each other to be able to determine some kind of analysis to look at a graph, perhaps. Okay, so the two things that we are considering in all of this that we've talked about is pressure and temperature. Because obviously we can change the volume, but the two key things we're looking at here is pressure and temperature. Now obviously in this particular case we're assuming, because obviously we're changing the temperature and then we're observing the pressure, okay, that this is a gas which is the same number of molecules, because obviously that will indicate a greater pressure. If there's more molecules, there's more than pushing out at the same temperature. Okay, so therefore we assume that this gas is going to be the have the same number of moles and molecules. Okay, as therefore obviously it's going to have the same mass throughout this experiment. Okay, so the graph we want to draw is going to look something like this, where we've got temperature on the x-axis, because as I say we're changing that. And for this case, I'm going to be observing it at degrees C. Okay, something like this. And on the y-axis here, we will have pressure. Obviously, pressure is always labelled in pascals. Okay, now the line I'm going to draw here, I'm just going to go ahead and draw it. Oh, actually no, I won't go ahead and draw it. Let's just see if you can see that on the camera first of all. If it's not too dark. Yeah, looks okay. Right, so the key thing here is how we're going to draw this graph. So let's again think of our ideal gas laws. Okay, so we've got that pressure is directly proportional to temperature. Okay. Actually, let's not go through them. This is the one, sorry, yeah. No, go through them all, because obviously we're looking at how pressure and temperature are related, and in the ideal gas laws, the pressure is directly proportional to temperature, which is obviously the same as saying temperature is directly proportional to pressure. They both mean the same thing, okay? So in other words, they're proportional to each other. So if they're proportional to each other, we're going to have a line of a constant gradient, okay? So therefore, the gradient is going to look something like this. Now, I'm not really going to go into any more detail on why this line looks the way it does than that, because, well, you just get these results from doing the experiment. Okay, so it's going to look something like this, because obviously it's just how it is. Okay, so temperature is the line is going to look something like this. This red line is kind of a constant line there. Hopefully you can see that. Now this point here, okay, God's sake, should knock something off there. To apologise. This point here, where the red line, which is the line of the points, okay, line of best fit of all the points, okay, that you might mark down of the pressure of a certain gas at different temperatures. If you did this as an experiment, it should look something like this. This point here, where it intercepts the x-axis, is the point of absolute zero. Which, if you do it right in the experiment, should be around 273 degrees Celsius. Okay, now, just want to go through a couple of things here. Okay, so as I said, absolute zero, just to recap what we've done so far, is where there's no kinetic energy of the molecules, there's no movement, so therefore there's no pressure. So we look on the graph for a point of absolute zero where there is no pressure, okay, and where it intersects the x-axis, in other words, where the y value is zero, okay, that is the point of absolute zero. And in this particular case, it's going to be -2, and in every case, sorry, for any gas, is going to be -273 degrees Celsius. Okay, so that's the theory of absolute zero. Now, the reason why we use Kelvin instead of degrees C to work this out, okay, is because Kelvin is a scale, okay, of measurement that goes from absolute zero. Okay, so when they created this idea of Kelvin, okay, anything positive Kelvin would be great. And that's why they call it absolute zero as opposed to absolute -273.15 degrees C. Okay, call it absolute zero because zero refers to the zero Kelvin. Okay, so that's why when we're looking at the difference between Kelvin and degrees C, okay, 0 Kelvin is actually equal to -273.15 degrees C, or -273 degrees C. Okay, that 0.15 is the specific value, okay, but you just round it down to -273 degrees C. Okay, so that's why the ratio is 0 Kelvin to -273 degrees C, because Kelvin is a reference to absolute zero, so therefore 0 Kelvin is absolute zero, and at absolute zero we have a temperature of -273.15 degrees C. Okay, so that's why when we convert to Kelvin from degrees C, we add or take 273 depending on which way around you're converting it. Okay, so hopefully that's a very quick analysis of absolute zero. If you want any further recap on this, please do ask for this note sheet I've got on all the key notes that I find are, having done physics A-level for 3 years, that these are the key points in second year that are the most difficult. Okay, so if there's, as I say, if there's any other questions, please do send me an email and I will shoot this one over to you with a few other revision guides that I've created and a few other past papers. Okay, so thanks for watching and we'll see you in the next video.